Today we're going to look at a different aspect of statistics, and just like, oh my goodness, permutations and combinations, this can get complicated. In fact, there are entire classes dedicated to it, but what we're going to do today is very simple. So we're going to start out. What is the definition of mean? Average. And how do we calculate average? And divide by n. In statistics, n is the number of terms. So, it's too bad. You don't get to pick. Oh, you don't need that. It's just average. Yes. What is the definition of median? Middle number. What if there isn't a middle number? Average of the two middle numbers. And when we say middle number, we mean when they're in order. That's kind of just inherent. Otherwise, it doesn't make any sense. What is the mode? Right, most frequent. What if there are two that are most frequent? It depends on who you're talking to. Some people say no mode. Some people say yes. Say they're both the mode, right. Because there's not a consensus, if you were to see this on the ACT or core test, it would be obvious. There would either be a mode or no mode. So there would either be 6 threes, or they would all be equal, in which case there would be no mode. But really, people don't totally agree on mode. What about range? Biggest number minus smallest number. All right. We're going to look at this set of data, so you can just watch this for a second. Now, I have put these scores up, and we're going to suppose that this was test A, test B, and test C. And we're going to calculate the mean, the median, and the mode of each of these. Oh, and the range. But I've made it super simple. If you look, they all have 370s. So the mode is going to be 70 in each one. And then the way that I've set these numbers up, how far is it from 29 to 7? Or sorry, how far is it from 41 to 70? 29. And then this is also 29. So don't write any of this down. So those two are going to average themselves out. Right? What is the average of 41 and 99? 70. Because they're both 29 from 70. So this 40 and that 100 are the same distance, and those are the same distance. So in this case, the mean is just 70. Okay, and if you didn't understand that, that's okay. Not a big deal. We'll look at the other lists. Well, I'm just saying I made it so it's 70. So if you look here, 40 and 100 match, 69 and 70 match, or 71, sorry. And then 68 and 72 match. So, oh, the median is 70. What's the range? 60. So, the mean, median, and mode and range are the same for test A and test B, right? What about test C? Well, we have 70s, 60 and 80 match, 50 and 90 match, 40 and 100 match, so they're all the same. So, what I'm showing you is, and again, if you didn't understand that, don't worry about it. Here are 3 lists of numbers that have the same median, mode, mean, and range. But they're definitely different lists, right? So mean, median, mode, and range can only tell us so much. In some of them, there are a lot of numbers close to 70. In another one, the numbers are spread out evenly, and in another one, they're spread out kind of on the edges. And yet, the mean, median, mode, and range are the same. And because of that, we need another measurement of numbers. We need some number that can tell us how spread out a particular list is. And that number is called the standard deviation. That's what we're going to study today. And again, it's super easy because calculating standard deviation is a pain in the butt unless you have a calculator. And I used to have to calculate it by hand in college. It was a mess. And then I asked my teacher if I could just bring a laptop and use Excel, and he said, oh, I don't see why not. So I did. Okay. Look back at your paper. I have a list of numbers here, and we could calculate mean, median, and mode, but I'm nicer than that. So turn your calculators on. We're going to do all of these calculations on the calculator. So all you have to do is put in the numbers, calculate, and then interpret. That's not going to work. I don't think that calculator can do it. It probably can, but I don't know how to do it. Definitely not. Yes, when I don't need your attention, that works fine. Okay, so everybody push stat. If you're watching, see the one with the red on it? Okay, and then push edit. Now, we need to clear list 1. We don't need to delete it. We need to clear it. So go up to L1 and push clear and push enter, and they go away. Now type in all of these numbers. Did I say clear list 2? Don't worry about it. So 2, 3, 5, 7, 8, Anybody having trouble with that? Figure it out, Peyton. Now, push stat again when you're done. And then go over to calc. And we've done this before. Remember when we did linear regression and quadratic regression, all that? So over in calc, we want to do one variable stats. So hit one variable stat and hit enter. And you get a bunch of symbols that you don't know what they mean. Okay. If you look further down on your worksheet, I have interpreted them. The top one, X bar, that's how we pronounce it. X bar represents the mean. So in this list, the mean is 10. And then lowercase sigma x, so it looks like this. That stands for the standard deviation. You don't know what the standard deviation is yet, but I'll explain it in a minute. So that's 5. And then if you scroll down, you can find the median is 10.5. Now, that's really nice because if you have a big list, you would have to reorder them in order to figure out what the median is, but your calculator will just tell you. You notice there was no middle number, so the median is the average of 10 and 11. And then mode isn't there. What was the mode? No, that's the range. What's the mode? 11. And to find the range, this will tell you the maximum and the minimum. So 18 minus 2. Now remember back when we learned about quadrants, and I said QI and Q1 are different? There's Q1 and Q3, and actually Q2 and 4 are in there too. They just have different names. So we'll learn about the quartiles a little bit later. So the range is, what is it, 16? Now, standard deviation. Mode was 11. It doesn't show up in the calculator. Yeah, mode's at the top. So, here is how standard deviation works. Okay? If you look at our list, right there, and we know that the mode is 10. The standard deviation is a measure of how far the numbers are away from 10. So 10 is the, sorry, did I say mode? I meant mean. The mean is 10. So if I look at these numbers, then I could do the number minus the mean, or the other way around. Let's do it the other way. So what is 10 minus 2? 8, 7, 5, 3, 2, 0, negative 1, negative 1, negative 3, negative 5, negative 7, and negative 8. You don't need to write this down. So this represents all of the distances. But distances are supposed to be positive. So we're just going to go through and we're going to square all of them. Now, I'm not going to. But by squaring them, I eliminate the negatives. Everybody agree? Now, I take those squares and I divide them. No, sorry. I add them all together, which is going to give me a really big number. So it's called the sum of the squares. You add up all the squares. Well, then I can take the sum of the squares and I can divide it by the total amount in the whole list. And then when I take the square root, that will give me the average distance from the mean. And it's a little more complicated than that, but when I finish this huge calculation, and it takes a while, I end up with one number, and that number is the average distance of each of the original numbers from 10. But it's not quite average distance because we squared them. So it's actually the sum of the squared differences. But that's not important. We're just gonna call it the average distance, even though it's technically a little bit different than that. So the standard deviation was 5. What that means is the numbers in the list, on average, are 5 units away from 10. Some of them are further than 5, and some of them are closer than 5. So these are further from 5, these are closer, and those are further from 5 than from 10. So the standard deviation measures how far are the numbers from the mean. Okay? So if we look at this list, which of the list is the most spread out? Which list would have the highest standard deviation? Well, let's think. Which has numbers that are further from 70? Connor? Well, if these were test scores, then we could grade them. F, 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 C, 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 A, A, A. F, D, D, C, 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 A, and F, F, D, C, C, B, A, A. So which one is going to have the biggest standard deviation? Which one has scores further away from 70 than the other two? So A would be the biggest standard deviation. Which one would have the largest? So this would be the large standard deviation. Does anybody not understand why? Oh my gosh. Oh, oh, you poor people who have to have me as a teacher. I'm sorry. No, I'm getting my second win. Yes, can I have a large bowl of salsa, please? And a big bag of chips? Okay, so one of the weird things about numbers, and this is kind of what Einstein was talking about when he did his big theorem, is that everything is relative. if I said a standard deviation is 5, is that a big standard deviation? Well, it depends. It depends on the numbers in the list. If I told you that a standard deviation was 1,000,000, is that big? Well, it depends. How big are the numbers in the list? So if we look back at this list of numbers has a standard deviation of 5. Is that big or small? Well, we don't really know yet. But I'm going to make changes to my list. I'm going to go back into stats, and I'm going to change everything and go up by 100. So I'm going to do 102, 103, 105, 107, 108, 110. Oops. Oh, that was too many. What was this one? What comes with 13? Oh man, I messed something up. And then two 111s. Okay. And then 130, 150, 170, and 180. Oh my gosh. 113, 115. Somebody else needs to teach this class. Okay, now I'm going to calculate my one variable statistics again, and the standard deviation didn't move. How come? Right, have the distances from the mean changed? My mean changed. What is my new mean? 110. So this list from 102 up to 118, x bar is 110. But has the distance from x bar changed? No, it's still 8, 7, 5, 3, 2, 0, 1, 1, 3, and so on. So in both of these lists, sigma x is equal to 5. Well, is 5 a big standard deviation? It depends. Is 5 a very big standard deviation for that mean? No, it's really small. Is 5 a big standard deviation for that list? It's huge. Well, let's think about the grades. So this would be 102, 103, 105, 107, and so on. If I gave a test out of 120, this grade would be a B, and a B, and a B, and a B, and then I'd end up with lots of A's. How spread out are those scores? Not very. If they're all A's and B's, they're not spread out at all. If this was a quiz out of 20, how spread out are the scores? F, 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 D, C, B, A. Out of 20. Those scores are very, very spread out. So 5 compared to 10. So 5 compared to the mean of 10, the standard deviation is about half of the mean, which is huge. Those are really spread out. It could get bigger. I mean, if you got rid of those 8s, 10s, 11s, and 13s and made bigger and smaller numbers, you could stretch the standard deviation. So it can get bigger, but having a standard deviation of 5 compared to a mean of 10 is really big. Having a standard deviation of 5 compared to a mean of 110 is really small. Those scores are very close together. So let's figure out the standard deviations for all of these lists. So go through and calculate standard deviation for A, B, and C. And we know that A is going to be the biggest, and B is going to be the largest, i.e. the smallest, and C is going to be somewhere in the middle. So go ahead and calculate those. Only Camry got that. Either that or she's the only one who gave me a pity laugh. Those were all mocking laughs. Those were not pity laughs. So for A, I had a sigma x calculation of 24.22. And here's a side note for those of you who end up taking a statistics class later on. See how there's a capital SX and a lowercase sigma x, and they're pretty close together? The bottom one is a standard deviation, and the top one is sort of a like an adjusted standard deviation. So if you're calculating a standard deviation for a list of numbers that you know, you just use sigma x. But if you're making a guess, like a prediction on future growth or something like that, then we've adopted this method of being careful, and instead of taking the average by dividing by n, we take the average by dividing by n minus 1. And that bumps our standard deviation up a little bit, and that covers any possible errors. So these two numbers are always going to be really close together. The more numbers in your set, the closer they are together, because dividing by 99 is almost like dividing by 100. But if your n value is really small, then those numbers are going to differ by a lot, because dividing by 3 is a lot different than dividing by 4. And I want to say that that's called the variance, but I've forgotten. It's been too long. Yes? No. Your order has no bearing on this at all. So if you make a mistake, then just put the one you're missing at the bottom. Okay. What did we get for the other two standard deviations? 14.18 and... Okay, so here's a question. Connor? Is this a big standard deviation? Well, compared to what? Compared to the other two, yes. So it's 24 compared to 70 is about 1/3. So they're pretty spread out. Yeah, that one's pretty big. Is test A more spread out than these numbers? Well, 24 is a lot bigger than 5, right? But remember, the 24 and the 5 don't mean anything without the mean. So these numbers have a standard deviation of 5 out of a mean of 10. And the other one is 24 out of 70. So which one has numbers that are more spread out? Is about 1/3. And the other one is 1/2. So these numbers are more spread out, which you can kind of see. Do we have lots of C's in this? No, it's mostly F's. There's one C, one D, one B, and one A. So there are a lot near the edges, and then as you come in, there aren't as many on the inside. So that's kind of how you can compare the spread outness of a particular list of numbers. For what? Spread outness? I believe that's a word. Okay, let me show you something else. Standard deviation is the most important calculation in statistics. It shows up everywhere. You have to know the standard deviation. Have you ever heard of an outlier? You've never heard the word outlier? Sometimes we study things like the size of antlers on mule deer, or how old people live, or all sorts of things. And most of the answers are somewhere near the middle, most of the data collected, but every once in a while you get one that's just way off to the side. And when something is way off to the side, it can pull the mean toward it. So if I was graphing the height of people, and I had all of these heights versus ages. And then I had one that was way out there, somebody who was really tall. Okay? My normal mean would be there. But because that one is so far away, it's going to pull my mean toward it. And it's going to skew the data to one side. So sometimes we include outliers, and sometimes we just say, forget it. That outlier we're going to ignore because it misrepresents the information. For example, you've seen those pest control or security system sales jobs, fly to Georgia, and it says the average wage is $20,000 in one summer. You've heard of those jobs, right? Have you known anybody who's went and worked one of them? Did they come home and not make any money? Well, what happens is you have a whole bunch of people, let's say 20 people, and they all make somewhere between $1,500 and $4,000 in a summer. So there are 20 of those. But the guy in charge of those 20 makes twice as much as all of these combined. So he might make something like $200,000. Well, when you average these, what's going to happen? So if I had 20 people who all earned $2,500, and I had one guy who made $200,000, and I'm going to divide that among how many people? Oh, shoot, I missed. So 50,000, oh my goodness, 50,000 plus 200,000. And there were 20 people who worked, 21 people who worked. So they say, hey, the average person made $12,000 last summer. Well, how many people made that much money? Just 1 out of 20. So that would be considered an outlier, and it's so far out there, it ruins the rest of the data. Well, how do you know if something is an outlier? How far is too far? Well, the answer basically is 2 standard deviations. So if I give a test, one person gets a 30, and everybody else is in the 60 to 100 range, how do I know if that's an outlier? Well, I find the standard deviation and I see how far it is. No, I don't, but statistically, that's what people say. So when you hear on the radio and somebody says, statistically, you're better off to do this than something else. Well, there are rules. You're only allowed to say statistically if you follow the rules. And I've taken 4 classes on that, so I'm going to spare you the details. But this one was 14.18, right? Well, is this number an outlier? Is it more than double the standard deviation from the mean? Yes. So actually, both of those are outliers. 14 times 2 is 28. Is 100 more than 28 from 70? Yes. So that would be considered an outlier. Is it a very strong outlier? Just barely. Well, it depends on what you're doing. It depends on what you're studying and what your purpose is, and sometimes people leave them in because it makes them look good, and sometimes they take them out because it makes them look good. So, did you ever hear Mark Twain's quote? I better. So, you can lie with statistics. If somebody came to you and said, the average wage for working 3 months is $12,000, would you like to go work for them? Yes, but are they being very honest? No, because they included the outlier. Now, if they excluded the outlier, would it give you a pretty good idea of what your chances are? Yeah. So sometimes outliers are left in, sometimes they're taken out. Sometimes they don't matter as much. But in this case, did the outliers affect anything? They did affect 2 numbers. They affected the standard deviation, because if I get rid of that and I get rid of that, my standard deviation is going to be like 1. So if I throw out the outliers, my standard deviation goes from 14 down to 1. What other piece of information did they ruin? The range. So without those numbers, the range is only 4. And that's how they judge it. Now let me give you another example. The ACT. There are like 11 versions of the ACT. I don't know, 12, 20, whatever it is. And the scores on each ACT test are different. Okay, and I'm going to oversimplify. Let's say that there are 100 questions on the ACT, which is not true, but we'll just suppose 100. And we'll say that the average score is 50, which is probably pretty accurate. Now, would you expect for there to be lots of scores in the middle or lots of scores on the edges? In the middle. And actually, it follows what is called a bell curve. That is called a normally distributed bell curve, meaning the mean is right in the middle. The mean and the median are really close together, and which means there's just as many numbers on the right and on the left, and most of them happen near the middle, as opposed to like an inverted bell curve, which would be like this. Lots of zeros, lots of 100s, very few 50s. So that particular bell curve would have a standard deviation. But the bell curve on test 2 looks a little different. So the bell curve on test 2 might look like this. Let's suppose that it's still in the middle. Which of those two curves has a larger standard deviation? Which one represents more spread out? The red one is more spread out. Right? The blue one is tight, which means the standard deviation is low. The red one is spread out, and the standard deviation is higher. So it's not really fair to grade these tests the same way, right? Because there are different standard deviations. It's harder to get a high score on the blue test than it is on the red test. So what they do is they create a bell curve. Have you ever heard grading on the curve? That's what it means. They create a bell curve and they say the average score is, I don't know, what is it, 20 on the ACT? I'm just guessing, 18? I don't know what it is. Let's say it's 18, because 18's, well, we'll do 18 because it makes more sense, because it's in the middle, okay? So there are not many 36s, and there are very few zeros. But the tests are not the same difficulty, or at least they don't have the same pattern of scoring. So what they do is they take sigma x from the red one, and they use sigma x to help score the red test so that you come up with this bell curve down here. And then they do the same thing with sigma x for the blue test. So if you got 75 questions right on the blue test, that might be worth, so 75 would be right here, that might be worth a 28. But a 75 on the red test would be worth more or less than that. Less than that. It might be worth 26. And they've done that with all of their tests, and it actually is very, very reliable. You're going to find out that it's hard to raise your ACT score, no matter which test you take. I mean, it takes a lot of work and a lot of practice because this method of curving the test allows for the scores that end up being the same no matter which test you take. Whether you take the easy test or the hard test, then you're going to end up with close to the same score because the standard deviation factors in the shape of the curve. Now, you might hear teachers say, oh, I curved the test. In a true curve, most people get C's, right? Most people are in the middle. They get C's. And then it's harder to get B's and D's than it is C's, and it's harder to get A's and F's, well, less likely to get A's and F's. So nobody really does true curving in school, but for tests, they do all the time. I don't know. Never been to law school. It's very possible for a law school to do it. So um, in core tests, they specifically write core tests so that 50 is the average. Because if it looked like this, oh, so if this was 0 and this was 100, that doesn't tell me very much, right? Most of the people did so well, there are probably things I didn't ask that they would have known. Does that make sense? It was too easy of a test. And if you had a curve that looked like this, nobody knew anything. So that doesn't help you prepare for next year. So all standardized tests, they try to write the test in such a way that it ends up being a normal bell curve. That way, these people did really well, and you know exactly where they did really well. As opposed to up here, you asked questions that were too easy, and you didn't get a good stretched out cross-section of the population. Does that make sense? Okay, so that was a very long-winded way to teach you how to do standard deviation. All you have to do tonight is go through these problems and plug them in your calculator and fill them out. There's one question that we didn't answer. And it says, what does the standard deviation mean in this case? So x bar was 10 and sigma x was 5. What does 5 tell us? So on average, the numbers were, say that again, Peyton? Okay, they're big, and who said the 5 units away from 10. Yes. Uh-huh. This is a model for all the other problems. So on average, the numbers in that list were 5 away from 10. And is that big or small? Well, that's pretty big. Could you make a bigger one? Yes. So it's all relative. Well, it depends. If it was 6 and 40, is that bigger or smaller? 6 is a lot smaller compared to 40 than 5 is to 10. But what if it was 6 and 7? That's huge. Could you make something bigger than that? Yes. You could do 6 and 6.1. So, could you have a standard deviation that's larger than the mean? Well, certainly. What if your average was 1? And if you had negative numbers, I mean, if your average was 0, you might have 1 and -1, 2 and -2, 3 and -3. Your average would be 0, but your standard deviation would be bigger than 0. So the standard deviation can be larger if the numbers can be negative. Nope. And that's a nice thing. Calculator does not care about order. Nope. So if you make a mistake, if you skip a number, just put it at the bottom. Yep. Good question.